thank you very much for being back. Where is my... Yes. So first of all, let me correct some typos, let's say. So I noticed that in some cases yesterday I wrote the wrong sign for this guy. So the right sign is this. So sometimes I was putting a minus here, which was not supposed to be there. I think most of the time I got the sign right, but okay, just to clarify. And also for the free energy, so I think I switched minuses for pluses, so there should be a plus. So well, this is in some sense intuitive, because you want to minimize the energy to be in the ground state of your system. All right, so now, so today we're going to essentially keep moving forward from where we left off yesterday. And we're going to build up to the Wimp Miracle and also up to exceptions to the Wimp Miracle. So we're going to see what's people's favorite dark matter candidate, or historically has been, and why, okay, this is not as much of a miracle as we were led to believe, but that changing tiny assumptions about the story, you can get exponentially different results. And when I say exponentially, I mean literally exponentially, with minimal tweaks. So this is the goal of the lecture today. There will be some part that is a bit more technical and boring, but we will have a prize at the end. So we will see that putting in very little effort, we're going to get out exponentially different results compared to what's the standard lore. Okay, so to get there, we have to pick up where we left off yesterday. And first of all, let me comment on this chemical potential. So this chemical potential essentially is telling you that you're paying a price to change the number of particles. But as you know, this is not always the case in quantum field theory. So for example, let's imagine that this process was in equilibrium. So this process is changing the number of positrons and electrons, the number of photons. So obviously, it cannot be the case that chemical potentials are all non-zero in this universe that we're describing, where the standard model is in thermal equilibrium. Indeed, so if processes like this are in equilibrium, meaning that the rate for going this way and the rate for going backwards are the same and are larger than the rate of the expansion of the universe, then you can show that there is this relation between chemical potentials. And another important thing that one can show, and I leave that to you as an exercise, is that the chemical potential for the photons is 0. And by photons, I mean anything that is relativistic. So anything that has an ideal gas equation that looks like this, and whose energy looks like a constant times t to the 4th. So this is a constant. And so as an exercise, I want you to prove this using these two facts. And OK, you can use F or any other thermodynamic potential that you like. And so in practice, this will mean that our life will be much simpler. So in many cases, this chemical potential here will disappear because objects will be in equilibrium with photons. And some terminology that's usually like taken for granted because of thermodynamics, but as you, like me, have forgotten, your second year teachings might be obscure, is that we're going to call particles that are in chemical equilibrium with the standard model are those that have chemical potential equals 0, in the sense that they are in equilibrium with photons. And we're going to call particles that are in kinetic equilibrium with the standard model those that have the same temperature as the photons. So we're going to call this kinetic equilibrium. And we're going to call this chemical equilibrium. All right. So as we said yesterday, so a universe that's in equilibrium all the time, it's boring. So it's essentially a dead bath of photons. with no features. And we said it in a rather end-wavy way. So the first thing I want to do today is to show you explicitly that this is the case. And to do that, we can use an equation that I think you've already seen. So essentially, conservation of energy in thermodynamics implies for the quantities that we were looking at yesterday what people call the continuity equation. And you can derive this also by combining the two Friedmann equations that we had yesterday. So this is also a consequence of GR, if you want, because it's nothing more than conservation of energy. And it's convenient to define this parameter W as P over rho. And this makes the equation very easy to solve. Because here Hubble is A dot over A. So you have, if you divide by rho on both sides, essentially you have d log rho dt is proportional to d log A dt with some constant factor like -3, 1 plus W. So in the end, the solution of this equation is very simple. It's just rho goes like A to the -3, 1 plus W. And so we're considering these baths of relativistic and non-relativistic particles. So for non-relativistic particle, the energy density is just some mass over the volume, and the pressure, we've seen yesterday that it's proportional to spatial momenta, and so it's roughly 0 at leading order. And so this W will also be roughly 0, meaning that rho scales like 1 over A cube. Okay? So we're already starting to see that in a universe that is expanding, everything gets diluted, so there is less and less energy around. For a relativistic particle, we didn't really see it very explicitly, but one can show that this holds. And so in practice, this would imply that rho is also going down like 1 over A to the 4th, so faster than before. Now, we haven't shown yet that the universe is expanding, because it's, well, there is some mutual interactions between gravity and energy. So gravity is determining how the universe is expanding or contracting, and at the same time, this changes the energy in the universe. So there is a system of coupled equations. But now that we've seen how rho scales with the scale factor, we can also solve more easily the first one of Friedmann's equation that, if you remember, looked like this in our universe where we experimentally established that curvature is small and the cosmological constant is irrelevant in practice until today. And so this equation, now we can rewrite it in this way. We picked some reference time 0, which can be anything you want. And so in practice, we have, again, a very simple equation that looks like just very similar to the continuity equation. I leave it to you as an exercise to solve it. It's relatively simple. And if you solve it, you can show that the scale factor goes like time to the 2 over 3 times 1 plus W. And so again, for the W's of ensembles of particles which are positive or at most 0, we see that the scale factor is growing. So now we've proven more rigorously the statements that we made at the end of the last lecture. So the universe grows with time, and as it grows, the energy density and the pressure are decreasing. To really close the circle completely, we want to see how the temperature scales with these parameters. In practice, we already have all the ingredients to understand how the universe evolves. But as a particle physicist, I find it more convenient to express quantities in terms of temperature that compares directly to masses and to scales that we care about, rather than do it as a function of time or scale factor, as some cosmologists like to do. So the last step is to understand how temperature scales with all that. And that's relatively simple, because we know that the entropy is constant. So if I compute the entropy at some time 1, at some time 2, I'm going to find the same result. And so it's convenient to define an entropy density as the total entropy divided by the volume, as we did before. And so this equation implies that the entropy density scales as with the scale factor cube. So the entropy density is going down like 1 over a to the minus 3. And so why is this interesting? This is interesting because we can compute this entropy density using the same thermodynamics relations that we've written down yesterday and today as a function of the energy density and the pressure. So if we want to be precise, you can find that the entropy density can be written in terms of the energy density plus the pressure minus the chemical potential minus the number density over T. And so this means that, as we shown yesterday, these quantities scale like T to the 4th, T cube, and T cube. So here we're talking about the total entropy density of the whole universe. So it's dominated by radiation, as we've seen yesterday, because all massive objects give contributions that are exponentially suppressed. And so this quantity will scale like temperature cube. So the first one will dominate, and this gives us a T cube. And so putting together this one and this one, we find that the temperature goes like the inverse scale factor. So we made all this work to finally just get to the very simple conclusion that as time goes by, the scale factor grows as some power of time, and the temperature goes down like 1 over the scale factor. And so at some point, so this temperature will cross the threshold, all the mass thresholds, and when this happens, all the massive particles will have number densities and energy densities that are exponentially suppressed. So we worked backwards to reconstruct what we said at the end of the lecture yesterday. So now that we have proof that a universe in equilibrium is boring, we want to see what happens. I mean, how can we get rid of equilibrium, let's say, or what's the physics of moving inside and outside of equilibrium? Because for now, we've put essentially zero physics in our derivations. We just said, OK, we know experimentally that the calculation of a universe in equilibrium at BBN gives us the results that we see today. And we've just used thermodynamics and countings of states to find very general formulae for what happens to energy densities and pressures in equilibrium. But how come that a particle can find itself in equilibrium with a thermal bath of photons? What are the interactions that determine that? And how these interactions fall in and out of equilibrium. So that's what we're going to see today. But before that, so I want to give you some better intuition for all this mess, right? So these equations are relatively simple, but are still kind of hard to remember as they are. So if you just write Hubble square equals 8 pi g Newton rho, okay, you might not remember it for the rest of your life. It's always useful when you see an equation to ask yourself what's essential about it. So this, if you want, is one of the most important equations that we've written down because it's telling us essentially how the universe evolves in the presence of some energy density. And so, well, what's essential about this equation is very simple. So there is g Newton, so which I like to remember like 1 over m Planck squared. There is the energy density, the total one, so that we said it's dominated by radiation, so t to the fourth. So that equation essentially is just telling us that for most of the history of the universe, Hubble looks like this. That's it. So if there is only one thing that you want to remember from the past 2 lectures, it's this one. Okay, so now let's see what happens with this equilibrium story. So more concretely, we want to see how does the density of particles change during the history of the universe. So how does it evolve in time? And we've seen that in equilibrium, we can write this number density in the following way. So this was all our efforts from today, from yesterday and part of today. Right? So if we wanted to write this in a more general way, we could write something like this. Where I traded the dependence on energy for a dependence on the magnitude of momentum, but okay, it's the same, obviously. And so this thing here is valid only in equilibrium, but this more general way of writing it, it's valid always in our homogeneous and isotropic universe, because the absolutely most general thing that you could write would be something like this. But we said already yesterday that the universe is approximately isotropic, so this cannot depend on the position where you look at. And it's also approximately homogeneous, so rotational invariant, so this guy can only depend on the only SO3 invariant that we have. So this second expression here is valid also when the particle is not in equilibrium. And so essentially, all we want to do is to compute the time derivative of this object f. And as we said, it depends on energy and time. And so, okay, just from elementary analysis, you know that its derivative is going to look like this. And people call this chain rule for derivation the Liouville operator. So I don't know why Liouville got credit for taking derivatives, but okay, I mean, they probably did something much more important, and that's the only little speck that we give him credit for. So the Liouville operator, okay, we can write it formally this way, but we can also use geodesic deviation in FRW to compute this derivative. And the result is this. And this derivation, I leave it to you as an exercise. So this, I even wrote the solutions in the notes, so when I'm going to share them, you can find the solution. But it's relatively easy. You just need to remember that you need to use geodesic deviation to get this thing right. So let's say that I want to start doing the easiest thing I can do. So just compute how many particles there are today, because this is relevant to see how much dark matter we have. So I don't really need to know all the details of the momentum distribution. I just want to know this integrated quantity. So the next thing I want to do is to integrate over the Liouville operator. So let's say I have some particle that I'm going to call 1. Then I want to know just this object. And again, this also, I leave it to you as an exercise, but I wrote the solution in the notes. You can show that the answer is this. And so in absence of interactions, this equation is telling you something that we already know. Because in absence of interactions, the time evolution, so the time derivative of the object should be 0. There is nothing that is changing the number of particles. And so this is just telling you how a quantity that we defined as number of particles over V evolves. So it's just following the expansion of the universe. So we can rewrite this equation in the following way. So again, we have a d log n equals minus 3 d log a. And so we know that the solution is, again, n goes like 1 over a cube, which is just what we expect, because distances are growing with the scale factor, and the volume is going down. The number of particles remains fixed because there are no interactions. So in its simplest incarnation, we can call this the simplest Boltzmann equation. That's what these kind of equations are called, are just telling us what we already knew, that if the number of particles is fixed, the number density is just being diluted by the expansion of the universe. So nice and easy. Now, well, let's say that there are interactions, because we know it's the case, at least for standard model particles. So if there are interactions, one can write an equation like this. So you can equate the Liouville operator to some other operator that people call the collision operator that is parameterizing everything that is going on. So this particle 1 might be interacting with a bunch of other particles. So depending on the nature of interactions, the look of this operator will change. So for instance, we can imagine that we have some simple 2-to-2 interactions. And actually, if there are no decays, there is even like a simple power argument in quantum field theory as of why this should dominate. This is the leading interaction. So the fewer legs you have, the more dominant an interaction is if you have a small coupling in your theory. And so this is the natural place to start. So the interaction with the smallest number of legs, at least in the case in which there is some symmetry that relates particles 1 and 2. So some, for example, Z2 symmetry. Okay? And we are secretly imposing this symmetry because we said yesterday that dark matter needs to be very long-lived. So the easiest way to make it long-lived is to make it stable. The easiest way to make it stable is to give it a quantum number that is conserved. And so if it has a quantum number that is conserved, it cannot decay. And this leaves us with the second most important interaction being 2-to-2. So where these two particles share these quantum numbers, let's say, so they have it equal and opposite. So in this case, we can write again, so the integrated version of this collision operator. And I'm just going to give it to you without proof, but we will try to disassemble its parts to see that intuitively they make sense. So there's going to be an integration over the initial state phase space, an integration over the final state phase space, times a matrix element for initial going to final squared, times F1, F2. No, sorry, let me delete. And, well, there is a sum over spins and a minus. So let me define for you these integrals over phase space. So I'm going to call the initial phase space the one of particle 1 and 2. And it's just the usual object that you have when you compute cross-sections. Then there is also a momentum-conserving delta function, which is there for the whole process. And I'm going to attach it, let's say, conventionally to the initial phase space. So that the final state phase space is the same as this guy for particles 3 and 4, but without the delta function, because you need to conserve momentum only once. Well, if you look at the rest of this object, what's going on is that you're asking essentially, so we are looking still at this equation. We integrated it, so the Liouville operator looks like this. So you're asking how interactions are making the number of particles 1 change with time. Okay? And here there is a minus in front of everything, which I don't know if you could see because I've written it pretty small. So of course, if particle 1 gets annihilated and goes into some other final state, this is decreasing the number of particles, so you have a minus. And the probability for this to happen is the usual invariant matrix element times how many particles you have in the initial species. I mean, if the universe had no particle 1 and 2 at all, clearly this process, the probability for this process would be 0. So you need something taking into account the fact that you need particle 1 and 2 to find each other in the vast expanse of the cosmos. Yes? Over the spins of everyone. So it's just because I'm just asking how many particles 1 there are. So I don't care about whether these particles have spin up, down, or anything. So everything that is changing the number of particles 1 is contributing to this collision operator. Then, okay, the second part is the same, only reversed. So if you have particles 3 and 4 going into 1 and 2, you are increasing the number of particle 1s. And this 1 plus or minus F3 and F4 are essentially taking into account the Pauli exclusion principle. So if these 3 and 4 were fermions and you had too many of them, this process would be suppressed because you couldn't make them, essentially, if all the phase space of the Fermi sphere would be full. So this is a bit the intuition behind this result. And now, well, compared to my traditional MO, I'm going to jump ahead by a lot. So I'm just going to give you the result for this integration. In some particular case, we're going to see where these results leads us in regards to dark matter, and then we're going to derive it to see what assumptions went in. So the result for this integrated collision operator can be written in the following way. These N1 and N2 are still the number densities, and these ones are the number densities in equilibrium. And this sigma times V, as the notation suggests, is a cross-section times velocity. And the angular brackets denote a thermal averaging. So this cross-section is averaged over all the possible momenta of particles N1 and 2 when they follow an equilibrium distribution. And we're going to better understand what this means once we derive the result. But before doing that, I want to tell you what this equation implies for dark matter. So what you're going to see next is the famous Wimp Miracle. And since I didn't tell you how I got this result, it will truly look like a miracle. So like we did the simplest possible thing. So we consistent with power counting in any quantum field theory. And then we will find out that dark matter might be possibly the simplest particle that we could think of. So now let me say that these particles 1 and 2 are the same. And they annihilate into some standard model particles that I'm not going to specify. Then the equation that we just written looks like this. So to simplify our lives, we can identify two regimes. So there is a regime where the expansion dominates over the interaction term. In this case, well, we are essentially solving this simplified version of the equation that we had at the beginning. So all that's going on is that the number of particles is fixed and the number density gets diluted as the universe expands. So if we define an nchi over entropy density object, this object in this limit will remain constant, because the entropy density essentially is eliminating the expansion of the universe from the number density. Okay? Well, in the opposite regime, what's happening is that these interactions are fast compared to the expansion of the universe. And this is valid for both processes, so the one that goes in this direction, but also the one that goes in the opposite direction. And this is the meaning of equilibrium. So when these processes are fast and happen at the same rate, then you cannot change the number of chi anymore. So you have to follow some equilibrium distribution. And so in this limit, the solution of the equation is that the number density of chi is equal to the equilibrium number density, which is the one that we wrote down yesterday. So if we were to plot this quantity, so the number of chi's where we factored out the expansion of the universe, let's say as a function of 1 over temperature, so time is increasing in this direction, we would see something like that. So first you follow an equilibrium distribution, and then at some point it becomes constant. So and this point is the boundary between these two regimes, which people call freeze out. So this is 1 over the temperature of freeze out. So here you see a bit more physically the meaning of equilibrium. So equilibrium means that the interactions of a particle with the standard model thermal bath are fast. When they become slower than the expansion of the universe, then equilibrium is lost. So the chi number density doesn't follow anymore an equilibrium distribution, but remains constant. And so you should be surprised at this point, because you see I'm equating Hubble to some cross-section. So let's imagine that this cross-section has some typical particle physics magnitude. So it comes from gauge interactions in the standard model. So by looking at the only thing you should remember from the previous lecture, so why is this story surprising? So what doesn't look completely right to you in this story? So Hubble, as you see, has an M-Planck, so it's dominated by gravitational interactions. And I'm imagining that this is dominated by some gauge or particle physics interaction. So naively, you might think that one always dominates over the other. Okay, so maybe either you already know the answer, or I'm jumping too fast to the conclusion. But okay, what I was getting at is that this object is much, much bigger than Hubble typically. So you would expect that this rate is huge compared to this other rate all the time, especially if you replace these number densities with the corresponding dimensional analysis result in terms of temperature. So here you have some particle physics cross-section times temperature to the 6. Here you have some gravitational interaction times temperature cube. So in the end, the particle physics interaction should always dominate. You should always be in equilibrium and die a sad death in a universe that's devoid of any feature except for photons. However, well, the answer is already in what we said yesterday, because at some point, this temperature will become smaller than the mass. And at that point, these ends become exponentially suppressed. So indeed, we have a chance to see the transition to this regime, because it's true that on one side we have gravity, and on the other side maybe we have a gauge interaction. But on the side of the gauge interaction, we have a double exponential suppression at some point in the history of the universe. So indeed, if you imagine a particle coupled through gauge interaction to the standard model, the story for its abundance would look more or less like this. And so we want to compute what's this constant value to which the abundance asymptotes, compare it to dark matter today, and see what this is telling us about the cross-section. So we have essentially established that there is only one moment in this equation that matters, which is what we call freeze out. So at that moment, so Hubble times the number density is roughly equal to the cross-section times the number density squared. So the number density at that moment is going to be roughly Hubble over cross-section. And we just said that this moment typically occurs only when the particle is non-relativistic, so when the temperature is smaller than the mass. So we can, even if we don't know exactly the definition of this object, we can always expand it in a small velocity expansion. And so here we're going to have our Hubble, so freeze out temperature squared over m Planck, times the leading term in this expansion. So what we know about dark matter is its energy density today. And the way I remember it, yes?
So what if I have like threshold or resonance and I can't expand it? Do I just have to do the integral, or is there another expansion?
There is another expansion, but well, maybe I'll try to show you when I write down the integral. Okay. But, yeah. So essentially, I mean, in that case, you can treat the cross-section in the integral like a delta function, or like a very narrow theta, and then the integral becomes easy to do. Yeah, so this is the number that we know. So now I'll tell you how I remember it. It's not maybe the best way for everyone to remember it, but it is for me. So what I remember is that at the time of matter radiation equality, well, the photons and dark matter had the same energy density. And this time was when the energy density was eV to the 4th. And so the dark matter energy density today is going to be eV times the temperature of today cube, because since then, it's been decreasing like 1 over the scale factor cube. So it's been decreasing like temperature cube. So at the time of matter radiation equality, the temperature was 1 electron volt. Today is what I'm going to call T0. So this is the dark matter energy density today. So what's the chi energy density today? The chi energy density today is the mass of chi times n chi at freeze out. And then we just need to redshift n chi from the time of freeze out until today. By redshift, I mean take into account the expansion of the universe. So again, we want to multiply it by the scale factor at freeze out over the scale factor today cube. And we've seen that we can trade these for entropy densities. And so we have mchi at freeze out times the entropy density at freeze out, sorry, the entropy density today, or the entropy density at freeze out. And we also saw that this entropy density scale approximately like T cube. So this is mchi, number density at freeze out, times temperature of today cubed divided by freeze out temperature cube. And so we can now plug in the expression for nchi at freeze out that we have back there. And we end up with mchi T0 cube over m Planck cross-section T freeze out. Okay? And now we're going to make another very rough approximation. So we're going to say that the temperature at freeze out is roughly the same as mchi. The reason is that, well, once the exponential suppression kicks in, things happen fast. So exponentials decrease or increase pretty fast. So we know that the freeze-out temperature cannot be too far from the dark matter mass. In practice, if you compute it, it's about a factor of 10 to 20, sorry, a factor, yeah, of 10 to 30, let's say, depending on the dark matter mass, below the mass. But, okay, we've been very cavalier with order 1 factors to really understand the parametrics. So there's no harm in doing this approximation. And so now we have the energy density in chi, and we want to see how it compares with the dark matter energy density today. So we have a T cube, T0 cube. We have another T0 cube. They cancel. And so we are left with this very simple expression, m Planck, sigma 0, electron volt. And we want this to be 1. If we want this to be 1, this is telling us that the cross-section should be about 1 over 10 TeV squared. And so here is what people call the Wimp Miracle. Because it turns out that this is roughly what you expect for a particle with weak interactions and a mass close to the weak scale. So if you imagine that there is a 100 GeV particle coupled through the weak interactions to the standard model, SBAM, you have dark matter, 0 effort. Okay? The beautiful thing, so the reason why, well, so the reason why I like the expression Wimp Miracle is that this story is completely insensitive to initial conditions, right? So you don't have to know how much dark matter there was at a temperature of m gat. You don't need to know anything except that this object has weak interactions with the standard model and that the universe existed at least at a temperature of order the mass. That's it, okay? So very mild dependence on initial conditions. The reason why instead I don't like at all the name miracle, so the reason why it's a crappy miracle in some sense, is what I didn't tell you about yet. So are all the assumptions that led to this expression for the Boltzmann equation. And this is what we're going to do next. So I think we're at half time now. So if you guys have questions, go ahead. And then we're going to see that this miracle doesn't really come for free. So you might be led to believe that it was a free miracle, but no. It was a miracle with at least 2 big hidden assumptions. Yes?
So when you say that it doesn't depend on initial conditions that much, do you mean that at some point you establish this thermal equilibrium and it just tracks it before it?
Exactly. So if you just imagine that this interaction is of order weak interactions and that the universe existed at a temperature large enough, then these were in equilibrium. So you can just compute it. And so this washes out. It doesn't matter what the dark matter density was at some initial point because it will go to equilibrium due to these processes. So whether it was 0, whether it was infinite, it would go to equilibrium, and then it would follow our calculation. Yeah, so that's what I meant. And this is, well, I would say that, OK, I think this is not stressed enough. This is the real unique feature about the Wimp miracle. There are not many dark matter mechanisms that can boast this insensitivity to initial conditions, and we will see about that soon. What's not such a miracle is how the weak scale comes out. In reality, this scale can be exponentially different than the weak scale, and we will see it in another half an hour. So any other questions? Yes?
Can you please repeat the last part of discussion when you went from one equation to the other one?
So from this guy?
This one.
OK, so we start from, so we want to compute how many chi's, so how much energy density in chi there is today. And so we said here that freeze out happens when chi is not relativistic. So its energy density is roughly the mass times how many chi's there are. OK, so this is an energy over a volume. This is a number of chi's over a volume. And from the moment these interactions freeze out, the number of chi's, so the total number of chi's remains constant. But the number density, so the number divided by the volume, is going to go down like the scale factor cube. Okay, so that's all I did here. So I just essentially accounted for the fact that the universe is a few 100,000 times bigger today than it was at freeze out. And then, OK, I used the fact that the total entropy is constant between, I mean, it's always constant. So the one at freeze out and the one today are the same. To write this ratio of scale factor as a ratio of entropy densities. So the entropy density is defined in this way. So it's the entropy times the scale factor cube. So it's really just a definition. And then I used the results that we had yesterday about how energy density, pressures, entropy densities, et cetera, scale in equilibrium to replace this ratio of entropy densities with a ratio of temperature cubes. So this is an approximate equality. So in reality, when you compute the total entropy density of the universe, you're summing over. So there is like some numerical factor. And then there is the same as we were seeing yesterday for Hubble. So there is some object that is essentially summing over all the particles that are relativistic. But we essentially neglected this order 1 factor in front, which is not really order 1. It can be order 10, 100. But I mean, the important thing here are the parametrics. And so we just replaced S with T cube. And then we substituted for the number of chi at freeze out what we got from saying that freeze out happens when the expansion and the interactions are comparable. And so freeze out is the time when the number of chi's is roughly given by the Hubble expansion over the cross-section. And for Hubble, we use that one, so T squared over m Planck to get this. For the cross-section, we use the expansion to get this. And so once we have this expression, we plugged it back in here. And so this gives us the amount of chi that we have today. So the amount of chi that we have today is T0 cube, which is the temperature today, over m Planck times the cross-section. And now we want to compare how much energy density there is in chi today to how much energy density we've measured in dark matter. This is just a number. But the way in which I remember it is this, that it's 1 eV times the temperature today. The temperature today is 0.1 millieV. So if you want, this is just, it's just this number. And so we are taking the ratio between this and EV times T0 cube, and we get this. So if we want these chi's to be all of the dark matter, this ratio needs to be 1. And this allows us to predict the cross-section. And then this fact, so that the number that comes out is equal to weak interactions over a weak mass, is just a coincidence. So in reality, you get the same amount of dark matter anywhere on some line of fixed cross-section. So we're just saying that coincidentally, the standard model already lives here, but in practice, you could get dark matter anywhere. So that's already the first reason why this is not such a miracle, because if you change the coupling, you can get a completely different mass. But, well, we will see more in a second. OK. Any more questions? OK. Then, OK, now we've seen the fun part. And we got a work for it. So we have to see the R part. So how we got to writing the collision operator in this way. So as we see what assumptions come in, we're also going to see where light particles are coming in. So keeping the promise of the title. So we were looking at this object. And we said that this looks like minus sum over spins, integral over phase space of initial particles, integral over space of final particles, times some matrix elements. So now we are back in the case with 3 particles, possibly different from each other. So the first assumption that we're going to make is that these particles 3 and 4 are in equilibrium with the standard model, both chemical and kinetic. This means in practice that F3 and 4 are equal to this. If this assumption is realized, then we said that we're starting when these interactions are in equilibrium. That's quite general because at the moment we don't know any interactions that are weaker than gravity. We even have some conjectures that lead us to believe that there are no interactions weaker than gravity. So we always expect a time in the history of the universe where interactions are going to be in equilibrium. And if these processes are in equilibrium, so this one and the inverse one, then there is a relation between the F's, so the phase space densities, which is the following. So this can be proven. I'm not going to prove it to you, but well, it's just a mathematical fact deriving from this assumption. So if really the final particles are in equilibrium and the process is in equilibrium, then this is also true. Furthermore, so if this is the case, so you'll see that we're making only a small mistake if we neglect the plus or minus here. Because if the energy of the particle is bigger than the temperature, well, this exponential is obviously much bigger than 1. If the energy is smaller than the temperature, well, this exponential is also bigger than 1. So the smallest this object can be is e to the 0. And so it's a very good approximation to write this quantity as e to the minus epsilon over t. And this e to the minus epsilon over t, for the same reason that we just said, only backwards, is typically smaller than 1. And so we're going to neglect the f's where there is a 1 sum to them. Okay? So this one assumption was very powerful because it allows us to use this relation, and also it allows us to neglect f's with respect to 1s. And so this dramatically simplifies our collision operator. Now the guy looks like much nicer than before. Okay, so at this point, we can move forward without making any further assumptions. We can just use unitarity. Unitarity is telling us that the sum over the spins of the integral over the final phase space of one of the two matrix elements is equal to, the same but inverted for the other guy. And OK, we're going to call this quantity. Here, I'm putting a delta function in both phase spaces, though. OK, so this is the matrix element integrated with a momentum-conserving delta function. So if you want to be more explicit, this will have our delta to the 4 with the integral over P1 and P2. Sorry, P3 and P4 are our final particles. And this guy will have the integrals over P1 and P2 with the delta function. Okay, so I'm using a definition that's slightly different than before. And sorry, we can write this object as the following way. So these G1 and G2 are the number of internal degrees of freedom of particles 1 and 2. So essentially, it's coming from the sum over the spin of the initial state. Sigma is the cross-section for 1, 2 going to 3, 4. So initial state going to final state. And this F is a kinematical factor that I'm not even going to tell you about because it's not that crucial. At this point, to arrive at our final result, we need only 2 more steps. So we define a velocity as F divided by energy 1 and energy 2. I didn't tell you what's F, but this quantity has dimensions of a velocity. And then we define our thermally average cross-section that we saw before as the following integral, so as was anticipated by a question. So this, you can see that this definition is already taking us close to the final result. But I've used equilibrium distributions for 1 and 2. And we know that 1 and 2 are not always in equilibrium. So this definition, in principle, would be useless if it wasn't for a second assumption that we're going to make. The second assumption that we're going to make is that 1 and 2 are in kinetic equilibrium with the standard model. If this is the case, again, one can prove that the Fs for 1 and 2 are proportional to the equilibrium distributions. And by equilibrium here, I mean also chemical equilibrium, okay? So this K is a constant number. And this F1, F2 equilibrium are these guys. So if this is the case, we can first use unitarity to write our collision operator in the following way. And then now this definition becomes useful because F1 and F2 are proportional to the equilibrium distributions. So in some sense, we can move out this integral. So it's a simple mathematical step that I invite you to do on your own. So you can use the fact that F1 and F2 are a constant times F1, F2 in equilibrium to rewrite this integral exactly in the same way that we did before. So we get to the final result. So if you want, this can be another exercise, but it's also in the notes. Yes?
Why we have minus sign?
Here, oh, sorry, here there is no minus, yes. Sorry, that was my bad. It's only that I kept writing minus in front of the sum over spins for everyone, and it just stuck in my head. But yeah. So anything else?
Also, isn't this detailed balance? You said it's unitarity.
So this is detailed balance.
Oh, it's done.
Yeah.
So that one follows.
This one is, so it doesn't care about the, sorry?
It's crossing symmetry? Or?
It's really, well, it has an element of crossing symmetry in it, indeed. But OK, so it doesn't have anything to do with equilibrium, non-equilibrium. There are no Fs. It's really a property of probabilities in quantum field theory. OK, so we've seen now how we got to the final equation that gave us the Wimp miracle. Sorry, anything else? No. Okay. Sorry, CP? No, well, no. It's more fundamental than CP. So even if you had CP violation, this would be true. Okay, so yeah, so we've seen how to get to our Wimp equation, and we've seen that there were a couple of assumptions that we made, and also again we made this choice of using yes, this fundamental property of quantum field theory to relate the two matrix elements. Okay. There are actually other hidden assumptions in this calculation. For example, we have implicitly assumed that that this process, so 1, 2 going to 3, 4, is allowed at 0 temperature, so that the sum of the masses of the initial states are bigger than the sum of the masses of the final state. Let's say that we start by relaxing this one assumption, which is kind of the simplest one that you can relax. So let's imagine that for some reason, so now I'm going to delete the first blackboard. Let's imagine that for some reason dark matter is lighter than the standard model particles that it's annihilating to. So we have the very same super simple 2-to-2 process, but now m chi is a bit smaller than m standard model. Okay? This doesn't mean that this process is forbidden because we are in a thermal bath. So as you can see, there will be tails of particles even at infinite energy. They are exponentially suppressed, but there are chi's that have enough kinetic energy to annihilate into 2 standard model particles. Okay? There are fewer and fewer as the temperature goes down, but there are some. So if you want, this also suggests to us a more physical way to understand what freeze out means. So if we go back to the story that we said before, where dark matter was lighter than the standard model particles, what was going on was that at some point, these two processes are not equally fast anymore. So at some point, the number of standard model particles that have enough kinetic energy to make 2 dark matters become exponentially small. So when this happens, essentially this process is not occurring anymore. But this process keeps happening. And so this is when you cross the temperature of the universe becomes smaller than the dark matter mass. So when this happens, then this process continues to occur, but this process stops effectively. And so you're dumping dark matter particles into standard model particles. And that's when the number of dark matter particles starts decreasing exponentially. At some point, you have so few chi's that you have less than 1 chi within your horizon. So in the universe, you're in causal contact with a region of size Hubble, roughly. So if there is only 1 chi per Hubble volume, or these chi's can never meet. Okay? So this is a bit extreme. This is actually happening way after freeze out. But you can imagine that freeze out is happening when there are so few chi's in an Hubble volume that they never meet in an Hubble time. And so at that point, effectively, also this process stops. And then the number of chi's is conserved. And so this is when chemical potential for chi becomes different from 0. And at that point, you cannot change the number of chi's for free anymore. But the physical picture is that at some point, you don't have enough energy to make chi's, but you still have enough chi's to make standard model. And then after that, you don't even have enough chi's to make standard model. So this is the physics behind the Wimp. Now, let's see what happens in this modified case. So I didn't make anything. I didn't do anything dramatic. So in principle, the calculation should be exactly the same as before. However, so this time, it's not so easy to calculate the thermal average integral for this process, right? Because I would have to really be able to do this integral for chi going to standard model. I cannot use my simple velocity expansion as I did before, because that process is not allowed at 0 velocity. So I really have to do this whole integral. But let's say I don't know how to do it. If I don't know how to do it, well, I can use a trick. So I can avoid using this property in an intermediate step, but continue from this equation. Okay, so the number of chi, so let's say that I want to do this integral now. Okay, so I'm gonna have I can easily do the integral over the standard model phase space of the matrix element for chi going to the standard model. So I have no integral over chi momenta, so I can factor out the number of chi's. And this is going to give me, as before, some kinematical factor times the cross-section. And for the second term, I can do the same, only this time I'm going to integrate over the chi phase space. And so I now can plug back these two results in the same derivation that we did before. And at the end, the equation is going to look like this. So I have minus okay, so now I'm left with this integral that I don't know how to compute, but I also have one guy that I know how to compute. And I can use the following trick. So in equilibrium, the rates for these two processes, so chi going to standard model and standard model going back to chi, have to be the same. So in equilibrium, I know that should be equal to the opposite process. Okay, yes. Sorry, this equation is also? Yes, yes. Yeah, so this is just another way of writing the same equation as before. It's just that it allows me to use this trick to compute the thermally averaged cross-section for this process. Yeah, so now, well, I can just, so I know the equilibrium values of the number densities. So essentially, I've established that this process is, so this guy is exponentially suppressed at freeze out, okay? So we're going to use the non-relativistic result. And so, yes, so did I do this right? Let me see, yes. And so, okay, I can use, so I can use the usual velocity expansion for the process, for the inverse process, which is allowed at 0 temperature. So here I can have some cross-section times n standard model in equilibrium squared. And so this object is going to be roughly at 0 temperature cross-section times an exponential, so of m chi minus m standard model over t times 2. Okay, so I'm imagining now that potentially also the standard model particles are non-relativistic at the same time as the dark matter. And I'm imagining this because well, otherwise, this exponential suppression would be too much. So this process would never be in equilibrium. Okay? So this story is valid if this mass difference is not order 1 with respect to the mass. Otherwise, you can show that the process is essentially never in equilibrium for the same reason that we've seen before, right? So the Wimp sooner or later freezes out, and the same would happen here almost immediately because you're starting with a process that's already exponentially suppressed. Okay, so I just told you that the process that matters to determine the relic density is chi going to standard model. So when you are computing the relic density, you can repeat the same that we did for the WIMP, but now your relevant cross-section has this exponential factor in it. Okay, so if we compare the cross-section that we need in this case with the cross-section that we needed for a WIMP, then we have an extra exponential factor. So this is telling us that the coupling and the masses here should give you something much smaller than what you had before. So if you write this as a coupling times a mass, well, here the standard model mass is bigger. Then, if you want the same relic density as before, you need a relation between coupling and mass that is exponentially different compared to what you had before. Since the standard model mass is the bigger one here, this exponential here, it's negative, so it's actually better to rewrite it as e to the minus 2 delta x. So x, let's define it as the dark matter mass over the temperature, and this delta, we can define it as the standard model mass minus the dark matter mass over the dark matter mass. So this is the relative mass difference. And so you can see here that if you want this ratio to be, say, order 1, let me say that you want to start with a chi that has the same mass as a WIMP. Okay? Then here you're going to have a ratio of couplings. Then you want your coupling for the same mass to be exponentially larger. So, of course, this in practice cannot be done in a theory that's theoretical under control, but the two cross-sections differ also by a mass. So here, you also have an m WIMP over m chi squared. So what this is telling you is that you can get the right dark matter abundance with a dark matter mass that is exponentially lighter than that of a WIMP. So you can see that relaxing very simple assumptions can lead to exponentially different results because the exponentials are already built in the calculation if you want. So their importance is a combination of the fact that you are in equilibrium, and so you have a Gaussian suppression of things that are too heavy, and the fact that gravity is so weak, so that the relevant regime for computing how much dark matter you have is when objects are not relativistic and so exponentially suppressed. Okay, so this was the first example that one can give of what is not so miraculous about the WIMP. This is known as forbidden dark matter. And it's in one, let's call it, seminal paper by Grist and Saclay in '89, where they essentially noticed that if there was a small mass difference between the two, you had to do the calculation differently. And then, well, a couple of us noticed that this works also if the exponential is big. So that you can use this to get exponentially lighter dark matter compared to the WIMP. And as an exercise, I leave you, okay, so in principle, you should object something at this point. But maybe after, I don't know, 1 hour and a half, you're exhausted. But I really haven't proven to you anything yet. So I haven't really proven to you that there is an exponential suppression, because there is a factor that I haven't proven to you that remains the same between the two calculations, right? So we're doing everything at some fixed temperature. So do you guys want to try to tell me what I didn't prove yet, which is going to be the exercise for you, by the way? Yes?
One thing is that you don't know if you are connected equilibrium, right? Because you don't check the scattering.
That's true, yes, but that one, I mean, you expect to, because as I said, I mean, I want something that is exponentially lighter, so the cross-section will all be bigger, and in this cross-section there is no suppression, right? So the masses on the two sides are the same. So, but yeah, but there is one more thing that I have not proven, which is crucial to the parametric estimate. So if you look at this equation, you should see it. So let's say that if you want to be more precise, I'm comparing the two cross sections at freeze out. Yes. Yeah, sure.
You don't know if the freeze out temperature is the same.
Yeah, exactly. You don't know if the freeze out temperature is the same, and since the cross sections are exponentially different, you might say, okay, why should they be the same? But your exercise is is to prove that in reality they are order 1 the same, so that the forbidden temperature is roughly the same as a WIMP. This is a freeze out, okay? I've called this big F the forbidden and this one WIMP. So modulo an order 1 factor, which is given by the mass difference, okay? So you can have, I don't know, a mass difference of order 30%. This is not going to change the freeze out temperature at all, but here it's going to give you a huge exponential suppression, because as some of you know, and as I mentioned before, this XF is typically of order 20 or 30 or something like that. So this is e to the minus 20 or something. So this is so this is your exercise. And now, well, okay, now we've opened a whole Pandora's box. So you see that it's pretty simple to mess with the WIMP and find something exponentially different. And so I'm going to give you a list of ways in which you can mess with the WIMP, but we're not going to look at all of them. So maybe before the list, well, since I've seen that you guys are suffering at this hour, I may be a bit more precise about what I did here. So here, I just rewrote the Boltzmann equation in a different way, which is valid also for the WIMP. And then I said that the rates of the two processes have to be equal in equilibrium. This is telling us that the rate for chi-chi going to standard model is exponentially smaller than the same rate if it was kinematically allowed. Okay, so this is the result. Okay, then I'm asking if really this process gives me dark matter today with the dark matter mass smaller than the standard model particle mass to which it's annihilating. So what do I need as a coupling to that to get the dark matter relic density today? And we've seen before that rho chi over rho dark matter is roughly 1 over m Planck sigma 0 times electron volt. So you want this to be order 1. But in this case, well, you have to replace this sigma 0 with the exponentially suppressed one. So now you have m Planck, say sigma 0 e to the minus 2 delta x at freeze out times electron volt. So now my sigma 0 that gives the right dark matter is not anymore 1 over 10 TV squared, but it's 1 over 10 to TV squared times e to the 2 delta xf. And as I was telling you, this XF can be between 10 and 30, roughly. This delta before this process is not anymore the relevant one can be between 0, roughly, and 1/3, roughly. Well, let's say even more, probably, even under 2/3. And so you can see that there is a huge difference between the prediction of this simple variation of the WIMP and of the WIMP itself. Okay, so here I had done it in a pretty messy way. This is the cleaner way to do it. And so, okay, now let's open Pandora's box. So all that we've done is to change the kinematics with respect to the WIMP. So we didn't even change the process. It's still 2 to 2, still 2 dark matters going to 2 standard models. There's still kinetic equilibrium, everything. The other thing that we can change is dynamics. So who said that this has to be a 2 to 2 process? Well, it's power counting in quantum field theory, but dark matter can also be part of a strongly coupled sector where maybe 3 to 2 processes dominate. And one example of this is known as SIMP, and you can find the references in the notes. Another thing that we can change is the thermal history. So we have done all our calculation with Hubble being T squared over m Planck, but this is true only if we are in a phase of radiation domination. Furthermore, we've assumed that this is true all the time, but as we've seen yesterday in some of your talks, it could very well be that the universe was dominated by matter at some point, or even by a late phase of inflation, and this, of course, changes completely our prediction. Another thing that you can change is the single chi hypothesis. So here maybe there's chi1 and chi2, and there's also all sorts of processes with 2 chi2s, 2 chi1s, etc., etc. And okay, the best exception in this case is known as co-annihilation. And this, in some sense, is an example similar to forbidden. So Grist and Seckel laid out how to compute the relic density, and we showed that you can get exponentially different results compared to a WIMP. Then you can change the assumption that the couplings of the WIMP are order of the weak scale. And, well, the story here is so simple that it can be summarized in a single plot. So if you change the prediction for the coupling, you also change the prediction for the mass, even if your calculation is exactly the same as a WIMP. And, OK, the nicest model of these are known as WIMP-less dark matter, or, yeah, freeze-in, which maybe we're going to talk about. Here, in freeze-in, the calculation is not exactly the same. We're going to see it either today, well, no, actually, tomorrow, because I'm done. So let me just write the last thing. The last thing that you can change is kinetic equilibrium, so as the question anticipated. And, well, in some sense, point 1 to 5 were already secretly known from the 90s, but no one had shown that they led to exponentially different predictions. So essentially, the calculations were always done for cases where the dark matter mass difference with respect to the standard model or to its partners was very small. So in practice, they were power law correction to the WIMP, if you want, just a small correction where you could expand that exponential. So what's modern about this story is that people have shown that these processes are the relevant ones for the amount of dark matter, even when you cannot expand the exponential, even when this exponential is a huge suppression. This last one, so relaxing kinetic equilibrium, instead is something truly new that we did in 2016. well, you will find the reference in the notes. And this is another case of an exponentially different prediction. Okay, so for forbidden, we've seen essentially that we can go here. So anywhere in this plane above the Wimp prediction can be covered. So you can have dark matter also in this huge region. And this one shows you the opposite. And the basic idea, well, and I'm going to finish, is that dark matter does something like this. So this process is a scattering process. So this idea is known as co-scattering. And I'm going to tell you next time where the exponential is hiding. But OK, if you want, you can try to tell me now. Well, there are two questions about this diagram. The first one is where the exponential is hiding. The second one is why this is wrong. So why this is not changing at all the amount of dark matter. And you can try to answer now. So you have 30 seconds. Or you can come back tomorrow and tell me the answer. And well, if I will, and then we will see what's the solution. Okay, so the promise is that there is an exponential hidden here, but that this diagram alone is doing nothing. And that's why it took from the 90s to today to understand how to leverage this exponential. But if you want, okay, the bottom line of these first two lectures is that we have a fantastically simple dark matter candidate, which is the Wimp. But if you relax simple assumptions in its calculation without writing any crazy theoretical model, you can get predictions that are exponentially different from a Wimp. This is sad, but it's still not as bad as what we started with. So if you remember, we started with essentially 100 orders of magnitude cube in mass, coupling to the standard model, coupling of dark matter to itself. Now we have a large parameter space. I haven't told you what are the boundaries yet. I will next time. But it's exponentially smaller than 100 orders of magnitude cube. So if this was the whole story, we would have an experimental target that we could hope to cover before, I would say, our grandchildren retire. Maybe even before our children retire. Or if governments decide to give us more money, even before we retire. So I would say that we made substantial progress. We went from 100 orders of magnitude cube to something that can be done with finite resources within our lifetimes. And, well, we've done so with minimal theoretical craziness, right? So essentially, we have a simple dark matter particle coupled to the standard model. And, well, next time we're going to, let's say, complete this picture with the boundaries of the parameter space and a couple more words on some of these exceptions. And then see that this is not the whole story, but dark matter could be also something completely different, much lighter and much more weakly coupled. Okay, sorry for running late. Thank you very much. Yes.
So a very basic question. Can you explain again why we always have to work with this sigma times v and not just with a very simple cross-section as we're used to? Or what's the difference?
Yes. So the difference is just that. So physically, okay, normally what you're used to is that you prepare an experiment where initial particles have some energy and possibly some polarization, and you know them. You control them in the laboratory. And so you're computing this cross-section with some, okay, there is going to be some spread in the energies if you have protons here, because you have to sum over the energies of the partons. But, okay, the initial state is kind of determined. Here, instead, the initial state is a thermal bath. So if you want, you have to replace the parton density functions with these equilibrium functions that are telling you what's the typical momentum of a particle in the bath. And that's it, essentially. So physically, you're just saying that you're averaging your cross-section over the probability distribution for the momenta of the initial particles. So that's why it's called thermally average. So if you want, it's the exact same that you do at the LHC, but you replace the PDFs with these other functions that tell you the momentum, the typical momenta of your particles in this thermal bath. No problem.